did this research at Yale with Professor Robert Frank, and I really enjoyed doing this. So I'm excited to share about what I've learned with you guys. So before I dive into what exactly is lottery ticket hypothesis, I want to start with a very common phenomena that you guys have encountered in the past as well in classical machine learning. So can anyone remind us what the phenomena of overfitting is, or throw it in the chat? So I have Roderick said training is better than validation, memorization over learning, memorizing the data. Yeah, exactly. So this happens when the train era keeps decreasing. So it's doing better and better on training data, but it starts to have increasing test loss because it's failing to generalize to unseen data. So as we can see in the graph here, at first, when we increase the parameters in a neural network, which represents its capacity, we start to do better and better. But after we pass a certain point, we can see that the test risk or test error starts to go back up, even though we continue to do better on training data. So one interesting phenomena when we enter the realm of deep learning is that what we see in classical machine learning is no longer true. So can anyone remind us what deep learning is, or give some examples of deep learning that we've seen in class before? Either shout it out or throw in the chat. So Anika said many layers of neural network. Yeah, exactly. So deep learning is essentially just machine learning, except we have much deeper neural networks, so a lot more layers. And what happens in deep learning is that even as we increase the capacity of the neural network, once we pass a certain threshold, which as you can see in the graph here, it's called the interpolation threshold when we have zero training era, the model actually starts to do better on unseen data as well. So we see that the test error starts to decrease, which is really, really strange. And so far, no one has a complete explanation for why that's the case, what makes deep learning special. So the work of lottery ticket hypothesis is proposed exactly to address or at least try to find an answer for this question of why does increasing the parameters more and more in neural networks continue to do so well in deep learning, even though it wasn't working in classical machine learning. And this line of work was originally proposed by MIT researchers Franco and Carbon, and it lies within a subfield of pruning within deep learning. So does anyone want to take a guess or take a shot at answering what the idea of pruning might be in neural networks? And as a hint, it's something similar to the dropout layers that you guys have worked with in the past. So what are we doing when we are pruning a neural network? Does anyone have any ideas? So Anika says setting more nodes to zero, maybe. Yeah, very great answer. So essentially when we prune a network, we can either prune neurons, which essentially means getting rid of all the connections connected with it. And that's what exactly dropout does during training. Alternatively, we can set the weights to zero. So that would be pruning the connection. So as we can see in the graph here, when we have this neural network, we can either get rid of the weights, which are the connections between the neurons, or we can get rid of the neurons themselves, which get rid of all the connections associated with it. So in lottery ticket hypothesis, what we'll be doing is pruning the connections or the weights. So what exactly did Franco and Carbon propose? Their hypothesis is that a deep neural network contains a much sparser subnetwork that has minimal loss in performance. And this subnetwork, it's lucky, so we call it the winning ticket or winning lottery. So if we take this example at the bottom here and imagine expanding to billions of parameters. So that takes us to a very high dimensional parameter space. And what Franco and Carbon are proposing is that this high dimensional parameter space already contains a much lower dimensional space that does the job equally well. And the process of training is essentially the process of carving out this low dimensional space. And without having so many parameters to start off with, it is harder to find this winning combinations of smaller, sparser network, which is why deep learning works well, but machine learning has the opposite effect. So in the follow-up work, they revised the criteria for winning ticket a little bit and said that the winning ticket is defined as those who perform a lot better than randomly initialized network of the same sparsity, where sparsity here essentially just means the number of unpruned weights over the number of total available weights if we didn't do the pruning. So I think this demo from Facebook AI Research is really great at demonstrating the process of generating a winning ticket. Can everyone still see my screen right now? Okay, cool. So yeah, we start off with the full network like before, and we train it so we can see the weights are being adjusted through like gradient descent, so it learns a good parameter. And then we'll be pruning the weights by a certain criteria so that we get a sparser network. Then what they're doing is they're resetting those weights back to the original random ones that they got for random initialization. So now we have the same basic network with the same values as we started off with in the very beginning, but it is a lot sparser because we have pruned a lot of connections in the neurons. And then taking this sparser network, we repeat the process of training it for, say, 10 to 20 training epochs. And then the weights will be a new set of weights that are a lot sparser than before. And here they actually claim that winning ticket has better performance, which is rarely the case, but this is for illustration only. And in comparison, we'll be training a random ticket of the same sparsity. And then we can see that the accuracy is a lot lower than the winning ticket. Cool. So just to reiterate, the process of getting a winning ticket is typically termed iterated pruning. So what exactly happens? We first train a randomly initialized neural network for example, 10 epochs, and then we save the initial random weights. Then we prune, say, 20% of the neural network weights to get a sparser network. We reset the weights to the saved initial random values. And then we retrain the sparser network for another 10 epochs. And then we want to make sure to freeze the pruned weights so that they don't become non-zero values again during training and gradient descent. And then taking the retrain network, we prune another 20% of the weights to get an even sparser network. And then we repeat this for a couple pruning iterations, let's say 30. And then at the end, we will have a network with 99.9% of the weights being gone. And if it is the winning ticket. So does anyone have any ideas about what criteria we might use for pruning the weights at the end of a training process? So remember that weights are just essentially values in a big matrix. So they can be large, they can be small, they can be positive, they can be negative. What do you think are some reasonable criteria for getting rid of a certain group of weights at the end of a training epoch? There are many answers here. So Leonardo said prune the smallest weights. Yeah, exactly. That is the most common one. So by magnitude, we can prune the 20% smallest weights. So Kikai said weights that have no effect on outcome. Yeah, so what that translates to might be the smallest weights because they don't really do much, or it might be the weights that have the biggest differences or the smallest differences from the first epoch in the training to the last epoch in the training. Because if they have very small differences, maybe they're not that important, or if they have really big differences, maybe they're too sensitive to the noise in the inputs, and we don't want that kind of sensitivity. So as you can see in the graph here below, this is from a paper by Uber Engineering, and they experimented with many different pruning criteria. So if you're interested, I would recommend checking their research out as well. So as we can see, the process of generating a winning ticket is really time consuming. We have to train a lot of epochs, and then we have to keep pruning and retraining. So a natural question that I asked is, does a winning ticket generated from training on one data set work well or when it's being transferred to another data set? So the answer is yes for image classification, according to some MIT researchers back in 2019. So recall that CFAR dataset is this image classification dataset where, for example, CFAR 10, we have 10 classes of a lot of images. CFAR 100 is another dataset with a lot more classes, so 100 classes to be specific, and fewer training images per class. And what they found, if we take a look at the graph here that they provided, is that at the bottom, we can see different colors in the plot correspond to different data sets where the winning ticket is generated from. And the red one is the random one, where it's just the same sparsity, but it's never being trained. So we can see that all the data sets that are generated from different data sets, all the tickets, and the same phenomenon occurs to other image classification data sets like CFAR 100, and they did it for a lot more data sets. And the commonality among all their experiment is that, yes, indeed, the winning ticket generated from one image classification data set does just as well on another data set that contains images that it's never seen before. So what I asked is, would the same phenomena occur in natural language processing? So what about on a task of language modeling, for example? And recall that language modeling has essentially two goals. The first goal is to predict the probability of the next word in a document or a paragraph. And the second goal is to compute the probability of a sequence of words, which you can get from the first goal as well. So they're sort of equivalent. And the network that I used is a variant of recurrent neural network that you guys may have briefly heard about in the NLP lecture. So essentially, recurrent neural network is great for text processing because it takes a variable length input and can output and can generate outputs that are of variable length as well. And so the network that I use is called long short-term memory network, LSTM. That is a pretty powerful variation of RNN. So what I did is that I trained LSTM on English language modeling dataset that comes from Processing Wikipedia. And I iteratively prune the network for 30 iterations. So earlier I said, if you do that for 30 iterations, you would have 99.9% of the weights pruned at the end. And then I transferred it to other language data sets like Hebrew, Italian, and Russian. And I compared its test loss with that of the random ticket with the same sparsity. And what I found that you can see in the plots below, that for Hebrew, Italian, Russian data sets, the random ticket continually performs worse than the winning ticket. And the gap in performance becomes even more prominent at the extreme levels of pruning. So what I found is that winning tickets generalize well, not only in computer vision, but also in natural language processing. And what that implication is that winning tickets have learned some sort of inductive bias that allows it to generalize across different tasks. And so that helps us understand a bit more about why winning tickets perform the way it is. And one part of its special property is that it has learned some inductive bias that are generalizable. So there are some additional directions in this field as well, and in my line of research. So for example, we can experiment with more Mandarin, Japanese, and other different languages. We can also experiment with changing a word order. So for instance, it might be interesting to see what happens if we do language modeling on reverse word order to see if the inductive bias that the winning tickets have learned may have to do with a specific word ordering, or does it generalize even when the word order is reversed. There are additional NLP tasks that we can look at in addition to language modeling, like text classification, text generation, etc. And then the most interesting direction, I think, is to dive a bit more into the representations of the winning tickets, which is what I'm doing now. So does anyone remember what PCA is, or how we might be able to sort of visualize the word embeddings of words? So at the end of the NLP lecture, you guys may have seen that PCA is a way to map high-dimensional word embedding vectors into lower dimensions so that it's easier for humans to visualize. And specifically, it tends to be like 2 to 3 dimension. So it would be interesting to see how the word embeddings that a winning ticket has learned may be more similar to the full network's word embeddings compared with that of a random ticket. So some additional concluding thoughts. Most work in this field is empirical because so far having those empirical research and empirical studies has been the most convenient and straightforward way for us to explore a bit more about winning tickets. But the motivation is fundamentally scientific because the goal is to deepen our understanding of what makes this special machine that's neural network work, especially in the realm of deep learning. Additionally, there are some potential downstream applications for having sparser networks that do not really have that much loss in performance. For example, sparser networks takes less memory, so it would be great for running inference on smaller devices that have limited memory, like VR headset or mobile devices. Additionally, in the future, we might be able to explore the sparsity in computation. So right now, CPUs can take advantage of sparsity to increase the computational speed. And in the future, it will be awesome to have GPUs and TPUs rely on sparsity to work a lot faster in training and testing.